Hello everyone, I hope you're having a good day. Today I'm going to teach you how to find the centroid of a shape by integration. We are going to be working through this shape together. And then you guys can find more solutions or more practice problems involving centroids by typing this link in your Google research search bar. Determine by direct integration the centroid of the area shown. Express your answers in terms of A and B. So here's the problem statement again. We will be going through the solution. So first step, we want to divide the graph into two curves, a green curve here and a purple curve here. And we want to find the area under each curve. For the green curve, we want to find this area. For the purple curve, we want to find this area. Basically for the green area, we want to solve for k first of all. 2b is equal to ka squared. And then basically, so why is that so? Because if we are taking this point over here, we see that the y coordinate of that point is 2b, and then the x coordinate is a. And then if we solve for k, we will find that k is equal to 2b over a squared. For the green area, we can then divide the green area into certain rectangles to approximate the area under the curve, like we do in integration. And then we can take, if we're using a right endpoint for approximation using these rectangles, we can find that the height of each individual rectangle is equal to y equals kx squared, the height of the curve. So, and then the x, the change in x is basically dx, which is a very, very small change in width. Like we see here, the area of an arbitrary rectangle. So the area, like we said, is kx squared times dx. When we're integrating, we let the width of each rectangle approach 0. So then we have the area under the curve. And we sum up all the individual very small rectangles by using this integration sign, which is an equivalent for the summation sign. But basically, we divide the curve into very, very small rectangles over here, all of width of a very small width, which we call dx. So basically, the green area can be approximated by, or it can be actually, this is the actual value, is the integral from first the lower bound, 0, to the upper bound, which is a. And then here we have it. For the second curve, the purple area, we can simply find the area of this shape by knowing the area for a triangle is equal to the base times the height divided by 2. So it'll be equal to a times b divided by 2. A times b divided by 2. Okay, so let's continue our solution with the third step. So the third step is finding the x and y coordinates of the centroid of each shape. Remember that we have a green area and a purple area. So remember those. Remember that our green area is this one over here. Well, our purple area is this little bit over here, the triangle. Anyways, basically, as we did earlier, we approximate by dividing the curve into different small rectangles, and then the distance of the centroid of each individual rectangle to the origin will be equal to x. And this is very important, as we can see. In approximating the centroid, and eventually approximating the centroid of this whole shape in orange, which we will call the capital X bar, and Y bar. First we want to find the x coordinate of the centroid for the first green shape multiplied by the area of the first green shape, and that will be equal to 0 to a integral from 0 to a of x times kx squared times dx. And I will tell you why. Because we previously, as we saw just previously now, we found that the distance to the centroid is x, as you can see. And then we want to multiply by the area. The area, as we found earlier, is simply equal to the y times the differential element. But we want an integration sign because we want to sum up all those individual elements. But this is simply how we find the centroid, by finding the distance of the centroid from the origin multiplied by the area. But it's simply that we are finding that for each individual rectangle over here, and then we are summing up all those values to find the overall centroid of this shape over here, of the first green shape, basically. So right now, this equation over here gives us the centroid of this green shape, whatever it may be. Okay, that much being said, we also know that the centroid of the second purple shape over here is equal to 4a over 3. And how do we get that? Well, we simply remembered the special formula for triangles. Basically, we know that the x-coordinate is 4a over 3 because this distance over here is a over 3. And then we simply add a over here. A plus a over 3 is then equal to 4a over 3. So the sum of the moments about the y, we need to do this to get the eccentric of the overall orange shape is equal to the eccentric of the overall shape multiplied by the integral from 0 to a times kx squared dx plus a times b over 2. Here we have the sum of the two areas of the two shapes, the sum of two areas. So basically the whole area under this shape over here. And this is in turn equal to the integral of 0 to a x times kx squared times dx plus 4a over 3 times ab over 2. Why is this so? Because basically this is the centroid. This is also the centroid combined with the area already, but this is the area of the triangle over here. So in each of these, we're multiplying the x-coordinate of the centroid by the area of the respective shape. Over here, we did this. X is a centroid. This is the area of the respective shape, except we need to sum all those up. So we can do a successive manipulation of the equation to find to keep simplifying down the equations and boil it down. And if you do this multiple times and then plug in k equals 2b over a2 like we found before, you should get eventually that x is equal to a. So basically the x-coordinate of the centroid for the whole resulting shape is equal to a. And now we will be finding the y-coordinate of the centroid by noting that for each individual shape, the y-coordinate of the centroid is y over 2. For a rectangle, it's like that. It's y over 2, the location of the centroid for a rectangle. Okay. So solution, we have all the steps now. We want to find the x and y coordinates of the centroid for each shape. First, we have that the y-coordinate of the centroid of the second shape, or wait, no, of the first shape, of the green shape again, that's why the equation is in green, multiplied by the area of the first green shape is equal to the integral from 0 to a times kx squared over 2 times kx squared times dx. Because as we saw earlier, this part corresponds to y over 2, the location of each centroid, and if you recall, y is equal to kx squared. So that's why we have kx squared over 2. And then kx squared times dx, as you will recall, is the dA. And then we have b over 3 times BA over 2, because B over 3 is the location of the centroid of the triangle, and then BA over 2 is the area of the triangle. If we go back here. If we go back here, you will note that the centroid of this triangle in the y direction is B over 3 because of how you find the centroid of a triangle. Next, we have the sum of the moments about y is equal to the x centroid times the integral from 0 to a times kx squared times dx plus a times b over 2, which is in turn equal to the integral from 0 to a times of kx squared over 2 times kx squared dx plus b over 3 times ba over 2. And this is simply a simplification of this equation over here. And sorry, this is supposed to be the sum of the moments about x, and this is supposed to be capital Y. But anyways, when we simplify down the equation, if we keep simplifying it down and plug in k, remember that k is equal to 2b over a squared. We should get that the y coordinate of the centroid is equal to 17b over 35. That is our final answer. Thank you guys so much for watching this video. I hope this video helped you understand how to do integration of centroids a little bit more. And I'll see you in another video.